We're now going to take a look at exponential functions, and right now we have the ability to find the derivative of e to the x, right? In fact, we know that particular rule. Let me just remind you of what it is. It's pretty hard to forget, but the derivative of e to the x is e to the x, right? So the question now that remains unanswered up to this point is, what if the base is not the number e? What about all the other exponential functions, right? What are their derivatives? And it turns out there's a simple result from algebra that allows us to answer that question. That result and the knowledge that we have from the chain rule, right? So let me first just do a little reminder of a couple basic facts about exponential functions from algebra, right? So an exponential function so an exponential function is one of the form, right? What do they look like? Well, they're of the form y equals a to the x, right? And now we can't just take any old number for the base a. Well, the base has to be positive, and the base cannot be equal to 1. Because if we have a base of 1, then we don't have an exponential function. In fact, what we have in that case would be a constant function, y equals 1, right? So that's the definition of an exponential function. Now, there are two change of base formulas from algebra. The one for logarithms, that one is very well known, but the one for exponential functions, unfortunately, is not very well known, right? So in other words, let's say you have an expression like this, a to the b, right? Where your base is, again, any number that's positive that's not equal to 1. Well, it turns out there's a change of base formula that allows me to convert this exponential expression to one that has base e. And the reason why that's helpful is because we know the derivative of our exponential function with base e. So if I were to take all my exponential functions and rewrite them so that they have base e, I should, in theory, know how to differentiate them. All right. So let's see what that looks like. And what we do is we take advantage of the fact that e and the natural log, so e and ln, are inverse functions. So if I take e to the power of ln of a to the b, then these two are exactly the same, right? Because we know that e and the ln, these are inverse functions, so they undo each other. So like if I take the natural log of a to the b and then take that result and raise e to that power, then I will end up getting this back. But if you notice, what happens is I've changed from a base of a to a base e. And then there's another way that this can be written using the property of exponents. I can take this b, right, this power, and bring it and put it in front of the ln as a coefficient. So it's e to the power b times the natural log of a, right? And this is known as the change of base formula, but for exponents, for exponential functions, right? So I'll just say that this is the change of base formula, not for ln's, not for logarithms, but for exponentials, right? So for exponentials. And it turns out this is all we need in order to be able to now write down the derivative of any function that looks like this. All right? Well, let's see how it works. So I'm going to take my y equals a to the x, and I'm going to apply this procedure and change it over to base e, right? So using this formula, we'll have that y equals a to the x. Well, that's equal to, again, if let's say we go through the steps that we have right here, this will be e to the ln of a to the x, right? So that's this middle step. And then since the x is an exponent, that property of logarithms allows me to take the x and put it as a multiple right here. So it will come down essentially and multiply the ln. So we have e to the x times the natural log of a. Now, why is this helpful? Well, in fact, let me even write it like this. Right now, since I have a product there, I have the commutative property, so I can write this as e to the ln of a times x. And since a is a constant, then the ln of a is also a constant. So this ends up being similar to like having an e to the 2x or e to the 10x or e to the negative 5x. This is just a constant. It just happens to have an ln there, right? And so it's not necessarily a rational number. It's quite likely an irrational number. But the thing is, we can find its derivative, right? So using the chain rule, in fact, just for a little variety, let's go back and use the first version of the chain rule. So using the chain rule, if we let u be equal to this expression here, our constant ln of a times x, then it means that y will be e to the u, right? And again, these two I can differentiate because again, this is just a constant. It's like having 2x, 5x, right? So let's write du dx. That's just going to be the constant natural log of a. And then when I differentiate my e function, again, using the result that we stated earlier and one that we've used many times now, the derivative of y with respect to u is e to the u. So then, putting this all together, dy dx is the product of the dy du times du dx. So that's going to give us e to the u times the natural log of a. And of course, we don't write our final answer in terms of u. We want the final answer in terms of x. So what do? Well, we plug the expression for u right here back in, right? And then what we're going to do is try to simplify it as much as possible. So if I have my e to the, again, put the ln of a times x back in the exponent. So we'll have the ln of a times x. But now we have this extra ln of a right here. Right? Well, let's reverse the steps, right? So let's switch this product around. So we have e to the x times the ln of a times the ln of a. Use the property of logs in reverse and bring the x back up and make it like a to the x. So we'll have e to the natural log of a to the x times the natural log of a. And again, use the fact that e and ln are inverse functions, so we end up having a to the x, but then times this natural log of a, right? And that's our derivative. So this is now the derivative of the exponential function a to the x. So we get back the a to the x, which is not surprising, but then we end up having this extra constant here because we now have a different base, right? So here's our summary of this result, right? So if y is equal to a to the x, then dy dx is a to the x times the natural log of a. And again, this is valid as long as a is a positive number that's not equal to 1, right? So now we have the ability to find the derivative of any exponential function, all right? So let's just do a few examples. And in fact, with the examples, let's combine not just this new result, but also, we recently worked on trigonometric functions. Maybe we can throw a couple trig functions in there as well, just to show that as soon as you have a new rule, it can then be combined with all the previous rules, right? But let's start out with something like this function. Let's say we have 20 to the x plus x to the 20th power. Right? And the reason I'm doing this is because I want to emphasize the difference between an exponential function versus a power function. So this is an exponential function. This is a power function. What's the difference? The difference is where the variable is located. In an exponential function, the variable x is in the exponent. In a power function, the variable x is in the base, and then that base is raised to a fixed power, right? And they both have different rules. To differentiate this term, we're going to have to use our new rule, and to differentiate this term, we'll use our standard power rule, right? So let's write down what the derivative is for this function. So dy dx. So now using our new rule, the base here is the base here is 20, or I should say a is equal to 20. So applying this result, the derivative of 20 to the x is going to be 20 to the x times the natural log of 20, right? And again, the natural log of 20 is some irrational number. The decimal expansion never terminates. There's no nice repeating pattern. So we tend to keep it like this unless we need a numerical approximation, right? And then plus, and then of course the derivative of x to the 20 using our power rule is 20 x to the 19th, right? So very different derivatives, and it's important to be able to recognize the different functions and then apply the appropriate rule, all right? All right, let's try a second example. Let's say we have something like y equals the sine of 3 to the x, all right? So this now is a composite. It is not a product, right? It's not a product. This is a composite. And again, we could use the first version of our chain rule, but let's see if we can apply the second version that doesn't require us to write down the u, right? So using our chain rule, we'll have dy dx. And we start by taking the derivative of the outer function. The derivative of the sine function is cosine. And we keep the inner function, so that's 3 to the x. And then we have to multiply by the derivative of 3 to the x. And this is what we just, that rule that we just derived allows us to write down that the derivative of 3 to the x is 3 to the x times the natural log of 3. Right? So whatever the base is, you take the natural log of that base, and that gives you the constant that needs to be multiplied. Right? So that's our derivative. And there's no real nice way. There's no way to combine these or simplify these, right? This is just what the derivative is, right? Let's try another one. So let's say we have something like 3x minus 5 to the x over let's say we have secant of 2x plus 1. All right. So now the functions are getting a little bit more complicated. Let's see what we're going to have. So we can differentiate this for sure. This will require our new rule, and then this will require a previously developed rule for the secant function. But then there's also this composite here. So there's so many rules that we're going to have to apply to write down this derivative. All right, let's take a look at it. So dy dx. Well, big picture is that this is a quotient, right? So the quotient rule says, in fact, let me write down what the quotient rule says. We have to take the derivative of the numerator, here we go, and then times the denominator. And again, the denominator is a binomial. It has two terms. So I'm going to put that in parentheses. And then minus the numerator, which is another quantity, so 3x minus 5 to the x, times the derivative of the bottom, which is, let me scroll a little bit more over, the secant of 2x plus 1, and then this is all over the bottom squared. Right, so this is our mighty quotient rule. All right, so what do we have left to do? Well, we have to evaluate that derivative, and we're going to have a pretty messy expression that, you can try to get clever with the algebra, and it just doesn't simplify nicely. It just doesn't, right? Okay, so let's see what this derivative is. So the derivative of 3x is 3, and then minus the derivative of 5 to the x is 5 to the x times the natural log of 5. Right? Now that has to remain in parentheses because, again, it's being multiplied by this quantity, which also I'm going to leave in parentheses. Right? And then this quantity also in parentheses. So we'll have 3x minus 5 to the x. Now, to differentiate the secant of 2x, we have to apply the chain rule. The derivative of secant is secant tangent. So it's secant of something times the tangent of something. But what is that something? Well, the chain rule says I have to keep the inner function. So the inner function here is 2x. So I have to put the 2x back in, and then I have to multiply by the derivative of 2x. So I have an extra 2 right there, right? So that little piece is the chain rule, and then this is all over secant of 2x plus 1 squared, right? And that's the derivative. You could go ahead and you can FOIL stuff out, but you're not going to have a lot of terms that will simplify. So I'm just going to leave it in this particular form, right? So again, some of the functions, even if they look relatively simple, their derivatives can look a lot more complicated. All right, let's try a couple more. Now this one, what I'm going to do is, so let's say y is, and I'm going to write down a simpler function, but it has a couple differences to it. So let's say it's 4 to the 2 minus 3x, right? Now, we could certainly just utilize the chain rule and say, okay, here is my inner function, call that my u. But what I'm going to show you is that this, using properties of exponents, could be rewritten so that it looks kind of like this form, like a constant times a to the power x, right? So I'm going to show you that this can be rewritten in this form, and once it's in this form, then it's easier to work with, right? So I don't need to use the chain rule, because all I need is the constant multiple rule and the rule that we just developed earlier for the derivative of a to the x, right? And plus, like I said, it's a good exercise in the properties of exponents. So the first thing I can do is this. I can write 4 to the power 2 minus 3x as 4 squared times 4 to the negative 3x. So this expression can be factored into this form. It has a factor of 4 squared and then another factor of 4 to the negative 3x. What rule am I using there? Well, the property of exponent that I'm using is this property, but I am using it in reverse. In other words, I have a single base raised to this, that's a sum. Well, I can factor it into a raised to this power times a raised to this power, right? So that's what we have there. But there's more, right? I feel like an infomercial, but wait, there's more. So we can definitely see that there's a 16 there. But again, this is not in the basic form of a to the power x because I have this negative 3 here. Well, it turns out, in fact, let me write down the rule that we're going to use here. If you have a to the mth power, then all of that raised to the nth power, then that simplifies as a to the m times n, right? Well, what I can do is I can say, well, this is like the m, and the x is like the n, and clearly here the a is 4. But I can rewrite it like this. I can make it 4 to the negative 3 power all to the x power, right? And now, so 4 to the negative 3 power, that is 1 over 4 to the positive 3 power all to the power x. And then one more step, and we get it, right? So it's 16 times, now 4 to the third power is 64, so this is 1 over 64 to the power x. So that's how we're able to rewrite this exponential function as a relatively simpler looking exponential function, right? And all of this is due to properties of exponents. I guess I should list the other one that I used here, going from this step to this step. A to the negative n is 1 over a to the n, right? So this is all algebra. Now let's do a little bit of calculus and find the derivative here, right? So dy dx is going to be, now this is a constant multiple, so we bring our constant multiple down. So we have 16 times, and now this is of the form a to the x, where a is 1 over 64. So when I differentiate 1 over 64 to the x power, I will get back 1 over 64 to the x power, but then I have to multiply by the derivative of the, or not the derivative, sorry, the natural log of the base. So the natural log of 1 over 64, right? And there we go. So that's the derivative in a slightly different form than what the original is. And sometimes with these exponential functions, you know, you look at this and then compare it to this and you're like, wow, are these things actually the same? Yeah, they are the same. But I think that this one is a little bit easier to differentiate, right? So along with a lot of these properties of exponents, and our new rule for differentiating functions of the form a to the x, we can now differentiate pretty much any type of exponential function, right? Next up, we're going to look at logarithmic functions and see what their derivatives involve. See you then.